Hey everyone, this video is going to look at some sample problems concerning inference about means. So we're just going to go through some examples together to look at these various types of problems. Okay, question 1. A specialty food company sells whole king salmon to various customers. The mean weight of these salmon is 35 pounds with a standard deviation of 2 pounds. The company ships them to restaurants in boxes of 4, to grocery stores in cartons of 16, and to discount outlets in pallets of 100. To forecast costs, the shipping department needs to estimate the standard deviation of the mean weight of the salmon in each type of shipping. So, first part, find the standard deviation of the mean weight of salmon in each type of shipment. So what we're going to look at, we know that for each one, they have, let's see, a box of 4. They have a carton with 16. And then they have a pallet of 100. Now, to find this standard deviation, we have a pretty simple formula for this. And the standard deviation for a sample, which is represented by Sx, is equal to the population standard deviation divided by the square root of n. So for each case, we're just going to calculate this for all of our samples. Now remember, for each one, let's see, we have a mean weight of 35, and the standard deviation they're saying is 2. So we're going to need to know this value. Now on, let's see, our box of 4, to calculate our sample standard deviation, we're going to do our population standard deviation divided by the square root of n. Well, we have 4 salmon in this box, so we're going to use 4. So this will give us 2 over 2, which gives us 1. So there's our standard deviation, 1 pound for a box of 4. Now for a carton of 16, 2 over square root of 16, which is 2 over 4. So our standard deviation here, half a pound. Then for a pallet of 100, 2 over the square root of 100, which is 2 over 10, so 0.2 pounds. So there is our standard deviation for each type of shipment. All right, back to the question. Then we have a second part. The distribution of the salmon weights turns out to be skewed to the high end. Would the distribution of shipping weights be better characterized by a normal model from the boxes or the pallets? Okay, so we want to know boxes or pallets. Which one would best give us, or give us the closest distribution to a normal model? And in this case, it would be the pallets. The central limit theorem tells us that no matter what population the sample is drawn from, the shape is approximately normal as long as the sample size is large enough. So, since our pallet has 100 fish, just based on the central limit theorem, that one is going to be more close to normal than the boxes would be, since the boxes have only 4 fish in each one. Okay, question 2. Using T-tables, software, or calculator, we need to estimate the following. So the first part, critical value of T for a 90% confidence interval. So let me get my table here. All right, so we've got 90% confidence and we want degrees of freedom of 17. So here's my table, and down the side we have our degrees of freedom, okay, down the side here. And then across the bottom, we have our confidence level. So it says that we want a 90% confidence level, and we want that for degrees of freedom of 17. So I'm just going to go to where these two values meet, and I get 1.740. So 1.74 is my critical value for t. Now, to show that in the calculator, what we're going to do is we are going to use the inverse t function. So for that, we go to second distribution. We're going to go to inverse t. And then the arguments that we have to put in for this, we have to put in the area, which this, if we're doing a 90% confidence interval, let's see, think about what this means. Okay, we're doing a 90% confidence interval. So if we've got our curve here, we want this area in here to be 90%. So to capture 90%, that means we're going, and if we want the middle 90%, we're going from 5% to 95%. So if we want to know what the critical value is, and here, this would represent our critical value, we need to use the area under that. So we're going to use 0.95 as our area. So back to our calculator, we're going to do 0.95. Then degrees of freedom, it said in the problem, was 17. And we're going to paste that into our inverse t. And we get 1.739, which the first time we got on the table, we got 1.74. So that would be pretty much right on. Okay, let's go back to our questions. Okay, the second part, find the critical value of t for a 98% confidence interval with degrees of freedom of 88. So again, looking at our table. Now, our degrees of freedom down here, once we get to such a large number of degrees of freedom, it's not just going to count by one. So we're going to have to go as close as we can to our actual degrees of freedom. So we're going to go to 80 for degrees of freedom because that's as close as we can get to 88. And we want a 98% confidence interval. So I'm going to find where 98% means 80, and I've got 2.374. So this value right here, 2.374. Now to show that in the calculator, again, we're going to go to our inverse t. And again, it asks for an area and it asks for degrees of freedom. So let's think back to our picture. Now we want to show 98%. So if we are containing 98% in this region, what are our cutoff values? That means we're only cutting off 2%. So this is going to be 1% and 99%. So we want to look at everything below. We want to look at the area below 99%, and that's going to give us our t value. So let's see, back to my calculator. I'm going to do 0.98, degrees of freedom, 88. And I get 2.08. Now, let's see. Oh, I typed it in wrong. It should have been 0.99. 0.99. Oh, now I've really messed it up. .99, degrees of freedom, 88. There we go, 2.369. And on our table, it was 2.374. Now you have to take into consideration that our table could not be extremely accurate with our degrees of freedom. So the table was just giving an estimate. So this one on the calculator is actually going to be the better choice. This is going to be closer to our actual value. So 2.369. Okay. Let's see here. Question 3. Describe how the shape, center, and spread of T models change as the number of degrees of freedom increase. Now, for this one you just got to kind of think about it. If we have degrees of freedom increasing, degrees of freedom is calculated by doing n-1. So that's our sample size minus 1. So as degrees of freedom increases, actually that means our sample size is increasing. And we've talked about sample size quite a lot so far in this course and how important it is, and how as your sample size goes up, everything gets a little bit more accurate. So I think it would be pretty safe to say, as our degrees of freedom increases, lots of things are going to get better concerning our T model. So I think it would be safe to say on this, our T model is going to become more symmetric, and then that means it's going to be bell-shaped. I think our center is going to be 0. The standard deviation will get smaller. And we saw that in the first example. As the number of fish in the box went up, the standard deviation got smaller. And basically, overall, it's just going to become closer to normal. So increasing our sample size and therefore increasing our degrees of freedom basically gives us a more normal curve. And our data is going to be a lot more, or our interpretation of all our data is going to be a lot more accurate. Number 4, the housing market has recovered slowly from the economic crisis of 2008. Recently, in one large community, realtors randomly sampled 36 bids from potential buyers to estimate the average loss in home value. The sample showed the average loss was $9,560, with, let's see, standard deviation of 1,500. What assumptions and conditions must be checked before finding the confidence interval, and how would you check them? Well, remember, we have 2 assumptions and conditions that have to be met. First one, we have the independence assumption. Now, for the independence assumption, we have to have our data have to be independent from one another. And to do that, the easiest way is to use a random sample. And it told us in this problem that they used a random sample, so we can check off the independence assumption. Then next we have our nearly, if I could spell, we have our nearly normal condition. And for our nearly normal condition, in order to check this, we would have to look at a histogram. Our histogram would allow us to see if it is unimodal and if it is symmetric. So we would want to see a histogram of these 36 samples that they collected to see if it's unimodal and to see if it is symmetric. Okay, so continuing with question 4, we're assuming that those assumptions and conditions have been met. So now, find a 95% confidence interval for the mean loss in value per home. Okay, so we want to do a 95% confidence interval for the mean loss in each home. Now, in order to do this, some of the things that we need to know from the problem. First of all, sample size was 36. Sample mean was 9,560. Standard deviation, 1,500. So based on this, degrees of freedom, we know is 35. And we're going to want our critical value. And this, you can get one of two ways. You can either get it from your table, or you can get it from the calculator. And if you're getting it from the calculator, it's inverse T. We're going to use the area below. So if we're doing a 95% confidence interval, we want this middle 95%. So that leaves 5% in each of the two tails combined. So that means we're leaving 2.5% in each place. So this is going to be 2.5, and this is going to be 97.5. So this is where our T, or our critical value, is going to come from. So under the curve, we need to do 0.975. Then we need to do degrees of freedom. So in our calculator, if we do that, we get 2.03. So that's going to be our critical value. Now back to confidence intervals. For our confidence interval, we're going to do x bar plus or minus critical value divided by our standard error, or times our standard error, sorry. So when we plug this information in, we're going to have 9,560 plus or minus 2.03 times 1,500 divided by square root of 36. And we could take and type in each one of these into our calculator. And if we do that, let's see, our 95% confidence interval is going to give us $9,052.50 to $10,067.50. Okay, so that's our 95% confidence interval. And remember, if you wanted to do this on the calculator, you are going to do, let's see, let's go to the calculator and we'll do it. Oops. We're going to go to T interval. So I'm going to go to Stat, Calc, and let's see. Oh, nope, I want to go to Tests. Sorry. T interval. We want to just enter some stats. So our X bar was, where is it? 9560. Standard deviation was 1500. N was 36. And we are doing a 95% confidence interval. And they give us 9,052 to 10,068. So if we compare that to what we just found, 9,052 to 10,068, we are pretty darn close. Now the last part of that question says, interpret this interval and explain what 95% confidence means in this context. So in this case, we are 95% confident that this interval that we just found contains the true mean loss per home. So each home, when it sells, we're saying we're 95% confident it's going to lose anywhere from $9,052 to $10,068 when it sells. Now the last question, number 5. A consumer advocate wants to collect a sample of jelly jars and measure the actual weight of the product in the container. He needs to collect enough data to construct a confidence interval with a margin of error of no more than 2 grams with 99% confidence. The standard deviation of these jars is usually 4 grams. What do you recommend for his sample size? Okay, so for this, let's see here. Here we go. For this, we've got basically just some general information that we got for this. The standard deviation for each jar was 4. He wants a margin of error of 2. We want 99% confidence. And we want to know how many jars should he sample. Well, we have this formula for margin of error. Whoopsie. And this formula says margin of error is equal to our t critical times our standard error, which is our standard deviation over our square root of our sample size. Now, some of these things we know. We already know the margin of error that he wants. We already know the standard deviation. We already know n. One thing that we will need also to fill into this table is our critical value. Now this, again, you can get from either your table or from your calculator. So I'm just going to look at my table real quick. I've got, let's see, 95% point. Oops. Hope if I looked at the right table. I'm going to do 2.576. Okay, 2.576. So now if we fill in what we know, 2 equals 2.576 times 4 over the square root of n. Now we've just got a little bit of algebra to do. So first thing I'm going to do, divide by 2.576. So this is going to give me 0.776 equals 4 over the square root of n. So now, multiply both sides by the square root of n. So I've got square root of n times 0.776 equals 4. Divide both sides by 0.776. And I get square root of n equals 5.15. So now, of course, I have to square both sides. So my approximation for n, 26.5. We always want to round up though, so we will say 27. We can't take half a sample, so we would just round that up then to 27 as our sample size. So those were just some of the inference about means problems. So hopefully you followed along pretty easily on those, and hopefully we were able to do those pretty well.